Welcome back. So this is lecture 41 in this course, Bayesian Data Analysis for Behavioral Sciences. In this lecture, I'm going to introduce you to Bayesian regression models. Um, so, so far what you have learned is that how do we set up a Bayesian model? So how do we define a Bayesian model in terms of its likelihood assumptions and prior assumptions? And how do we fit this model to the data? Which means basically how do we estimate model parameters. Okay, so this is what you have done so far. You now know how to specify your likelihood assumption and prior assumptions, and then how to fit the model to the data to estimate model parameters. And in this case we are estimating posterior distribution of model parameters. Okay, so which is fine so far. So now you know what a model is, what a Bayesian model is, and how to define your Bayesian model. Okay, now, in the remaining part of this course, we are going to learn how to apply this knowledge to theory testing or hypothesis testing or some sort of or other kind of inference that you want to make given the data, right? So we will see applications of the tools that we have developed so far. Okay. So first application is that you can do regression modeling using Bayesian inference tools that you have learned. Okay. So what is regression modeling and why it is important? So let me just illustrate with an example. Okay. So suppose you are doing an experiment where the task of the participant is to read a sentence on the screen. So let's say the dogs arrived, something like that. So there is some sentence on a screen. Participants have to read this sentence and they have to judge whether it's an acceptable sentence in English or not. So whether it's a good acceptable sentence according to grammar and semantics, or it is not an acceptable sentence. So they have to judge that how good is this sentence. Okay. And let's say they judge it using two keys. So two keyboard keys, either left, right, or whatever you decide, right? So they make a judgment with yes or no. So if it is a good acceptable sentence, they would say yes. If it is not acceptable, they would press a key and say no, right? So that's the response we are recording. But what we are interested in really is that how much time do they take to make this judgment? How much time do they take to judge a sentence? Okay. We have taken similar example before, right? Let us call it judgment time. Okay, let us call it judgment time. Okay, or reaction time, whatever you want to call it. Okay. Now, suppose we want to model these reaction times or judgment times on the sentence acceptability task, right? So based on whatever you know so far, let me know how would you do it. How would you model these judgment times using a Bayesian model? How would you estimate model parameters, and how would you draw inference about the underlying process? Okay, so the workflow is like this. This is what we have learned so far. We will define, the first step is specify likelihood and prior assumptions. Basically, we are specifying model assumptions. So I should write specify model assumptions. Okay, and what assumptions we need to specify? The likelihood assumption and the prior assumption. What is likelihood assumption? We need to make an assumption about the underlying distribution of the outcome variable. What is the outcome variable here? Reaction times, so judgment times. So we need to make an assumption about what is the underlying distribution behind reaction times in the ith trial. So let us say we assume that reaction time in the ith trial comes from a normal distribution with mean mu I, or it's a mu, and standard deviation sigma, where mu is the average reaction time across all trials, or average reaction time of the population. So whenever you recruit participants from this particular population, their average reaction time on sentence acceptability task will be mu. So that's how you can interpret this parameter. and sigma is their standard deviation at the population level. Okay, so this is likelihood assumption. Now you need priors on your parameters, so you can call it prior assumption. Okay, so you need two prior assumptions, one for parameter mu, another for sigma. So let's say for parameter mu, you assume that mu comes from a normal distribution with mean 300, standard deviation 50. This is fine because average reaction time in this case could be somewhere between, let's say, 200 and 400 milliseconds, which is a reasonable assumption. Of course, in one of the lectures, we will see the art of eliciting priors in more detail. I think we have done it already in one of the lectures, but we can see this for regression models as well. Now for sigma, let's say I decide a truncated normal prior with mean 0 and a standard deviation of 50. Okay, so these are reasonable prior assumptions here. So what I have done in the first step, I have specified model assumptions. What I would do in the second step, I can, for example, do prior predictive checks. So for example, generate prior predictions from the model. Do you remember how we generate prior predictions from the model? Basically, you will sample your parameters mu and sigma from their prior, right? And then based on these proposals from the priors, you will generate data, basically n number of trials from the likelihood function. So basically data generative function conditional on mu star and sigma star. Okay, so that's how you can generate prior predictive data sets, right? So this is the process, right? So these are two steps so far. Okay, what we will do in the next step, step 3 would be, so you have now model assumptions. You have also visualized how the prior predictions of the model look like. Now you will have data. Now you will actually do the experiment and you'll get some data. And let's say your data is y1 to n. Okay. Now given this data, you can estimate model parameters. So the third step is parameter estimation. And we have learned several techniques of doing parameter estimation. So for example, the sophisticated ones are Markov chain Monte Carlo and Hamiltonian Monte Carlo. And we also saw that there is a package in R and Python which can directly implement an HMC sampler for you. You don't need to write a separate HMC sampler. It can implement the HMC sampler for you. Okay, so which is the BRMS package, right? So you need to estimate model parameters. So in this case, we need to estimate posterior distribution of mu given the data y1 to n and posterior distribution of sigma given the data y1 to n, right? How do we do this? You can do it using, let's say, BRM function where you give your reaction time outcome variable given 1, family Gaussian because that was your likelihood, right? And you can define your priors, right? This is how you can estimate these model parameters. Okay, once you have estimated parameters, basically half of the work is done. Only thing that remains after this is that you should compare this model against a competing set of assumptions or against a competing model in order to make a claim, that there is evidence for this model or not, right? Because in order to make a claim about evidence or claim about any hypothesis, the claim is always relative to something else. You can only claim that whether your model is closer to the truth compared to some other model. Okay, you cannot make a claim based on absolute distance between your model and the truth, right? Because that wouldn't make any sense. We always make this claim relative to some other model. Okay, so that will take us to the fourth step, which is model comparison. Right now we are not going to go into model comparison. There will be separate lectures for model comparison, but just as you know that now in model comparison, what you can have is something like this. So let's say there is another model for the same data that some other researcher is claiming, or you are claiming yourself, that let's say RTIs are coming from let's say normal mu sigma, where mu has prior normal 350 and sigma is strictly equal to, let's say, 30. So something like this. Now these two models are slightly different in terms of assumptions about sigma, right? You can have other kind of differences between models as well, right? Then you can do model comparison and quantify whether your model is better than this competing model or not. Okay, so let's say this is competing model. Okay, so this is the workflow of Bayesian inference. This is what we've learned so far. Okay, now this is fine. Let us come back to the original problem, right? So this was the problem, that there is something written on the screen, right? And the participant has to give a judgment whether this is an acceptable sentence or not, and we are recording their judgment times, right? So we will produce a yes and no response, and we are recording judgment times. Okay, so how fast they make a judgment whether it's acceptable sentence or not, right? And we developed a model. We said that RTIs probably comes from a normal distribution with mean mu, standard deviation sigma, where mu has prior normal 350, sigma has prior truncated normal 050. Okay? So this was our model. Now, suppose someone claims that because a single participant is seeing multiple sentences, multiple trials, one after the other, right? So every participant is seeing, let's say, 500 sentences. Someone claims that as participants see more and more sentences, their speed of judgment increases because they are getting better and better at this task. This is called a practice effect. So there could be a practice effect such that as individuals see more and more sentences, they get better and better at this task. So they make faster judgments. Now they quickly can um, say that whether it's acceptable sentence or not. Okay, so that's the hypothesis. We don't know whether it's true or not, but someone makes this hypothesis that as participants see more and more sentences, they will get better at this task, right? So their judgment time should increase as the trial ID increases, right? So as you go from trial 1 to 500, their judgment times should get faster. So basically the judgment should get faster. That means judgment times itself should get smaller, right? So a smaller judgment time would mean that they are getting faster, right? So how do we specify this particular hypothesis? So how we let's say write this particular hypothesis as a Bayesian model? Can you think of it? Can you write this hypothesis within this model? That on average, judgment times will get smaller as trial ID increases. Okay, so you can again listen to this statement carefully, that on average, judgment times will get faster as trial ID increases. How do we encode this assumption within this Bayesian model? Okay. So let's see. What you have assumed is this, that reaction time or judgment time in the ith trial comes from a normal distribution with mean judgment time mu. So this is judgment time of entire population whenever they see this particular type of sentences, and sigma. Okay, I is indicating ith trial, by the way. Right? What this model currently assuming is that there is some, of course, some randomness across these trials, right? Because of they are coming from Gaussian process, so there is randomness across the trials, but the average reaction time remains constant across all trials. So this mu, parameter mu, which is indicating average reaction time or average judgment time, remains constant across trials, right? And this RTI is just indicating some random variation. It is not systematic variation, by the way. This statement does not mean that reaction time would increase as trial ID increases. This only means that on average reaction times remains constant. There is only random variation across trials. So some trials they could be faster, some trials they could be slower than mu, sometimes they could be faster than mu. Okay. So how do we encode the hypothesis that we were talking about? That on average judgment times get faster as trial ID increases, as you go from first trial to 500th trial, right? The way to do this is like this, because we are making a statement about average reaction time. So what if I assume that reaction time in ith trial comes from Gaussian distribution with average reaction time for that trial being mu I. So now mu I is basically not a constant, it is changing trial by trial. Okay, so the average reaction time is not constant across trials. Okay, so it is changing with trial ID. Okay, how it is changing with trial ID, that you will need to define in a separate statement. So let's say for now I write mu I is a function of trial ID. Okay, so trial ID is 1, 2, 3, 4, 5, 6 like that. Okay, so it's a function of trial ID, mu I. Okay, what kind of function? Well, you can define different kinds of function, but let us begin with simple linear function. So let's say mu I is a simple linear function of trial ID. How? So let's say as you increase trial ID by 1 unit, okay, mu I increases by this much beta. Okay, so as you go from trial ID 1 to 2, mu I increases by this much extent beta, right? So this is the increase in average reaction time per unit increase in trial ID. So with every trial, how much average reaction time increases or decreases? So if its value is negative, that means the average reaction time decreases, otherwise increases, right? So we have defined it like this. Now of course you will need another parameter alpha, which will give you average reaction time at 0th trial, right? So let's say before even you begin to see these trials in this particular task, right? So this is more like an abstract parameters, but the role of this parameter is to control the intercept. So remember, if you recognize this equation, this is the equation of a straight line, right? Do you remember these statements? Y is equals to mx plus c. And how do we plot this line? How do we plot the graph of this? If x is here, y is here, the graph looks like this. This point where this straight line cuts the y-axis is called the intercept, and the height of this point from x-axis is c. So this is your intercept. M is actually the slope of this line. So how do we calculate slope, by the way? If you are given 2 points on a line, it's y2 minus y1 divided by x2 minus x1. So it's the rate of change in y with respect to x. To what extent the value of y changes per unit change in value of x. Okay, so that's your slope. Okay. So it basically tells you the steepness of the line. So if slope is large, that means line is really steep. So something like this. If slope is very small, then line is slightly flat. Okay, so that's what slope tells you, that how steep is this line. Okay, this is exactly the idea we are using here. So mu I, your parameter mu, is increasing or decreasing with respect to trial ID. That will depend on value of beta. If beta is negative, it would decrease. If beta is positive, it would increase. So mu I is changing with respect to trial ID, and it is changing linearly. So basically it is the relationship between mu I and trial ID is same as a straight line equation, right? So we are writing a straight line equation here. So if you want to write this on a graph, if trial ID is here on x-axis and mu I is here on y-axis, then the graph is like this. This intercept is alpha. The slope of this line is actually beta. Okay, and beta tells you to what extent the average reaction time, basically mu I, changes with respect to trial ID. Okay. To what extent average reaction time changes as trial ID changes, right? That's what the parameter beta indicates, right? So this is what we have done. We have changed our model, or our likelihood function to be more precise. We have changed our likelihood function to this. In order to do what? To encode the hypothesis that on average reaction time gets faster or changes when the trial ID changes, to hypothesize the practice effect, right? What it did, it changed our likelihood assumption, right? So now likelihood assumption is not a single statement anymore. It consists of two statements. That RTI comes from normal mu I sigma, where mu I itself is equals to beta into trial ID plus alpha. Okay. Now you tell me how many parameters are here in this particular model. So how many parameters are there in this likelihood function? So this entire thing is a likelihood function now. So how many parameters are there in this likelihood function? One parameter is of course sigma. Okay, so that still remains, and you can have the same prior on sigma. Let's say normal plus 0.50, truncated normal prior 0.50. So it allows values between 0 and 100. What are the other parameters? Now mu I is not a parameter anymore because it itself is a function of different predictors and parameters, right? So it's not a parameter in itself because it is not some it is not going to have some constant value across trials, right? What are the parameters? Parameters are actually beta and alpha. These are new parameters for this particular model, beta and alpha. What is alpha? It's the average judgment time at trial ID 0. So suppose, so you can think about it like this: when you haven't even started doing this task, there is some average reaction time for the population, right? So you can have the same priors as you had earlier for the mu parameter on this, right? So let's say normal 350. Okay. So that's the prior on the intercept. What is beta? Beta is telling you to what extent average reaction time mu I changes with respect to trial ID. Okay. Now one important thing about beta is that when you are not sure whether these average reaction times will increase or decrease with trial ID, okay, it is always better to allow both possibilities, that could increase as well as decrease, unless your theory is such that it has to be positive or negative and you want to test it against a possibility of having 0 or negative, right? Unless you are doing systematic comparison for parameter beta, you can allow it to vary in both directions. So that means you can set up a prior like this. So let's say normal 0, 10 or 0, 20. Let's say 0, 10 is fine. What it tells you is that average reaction time can change by what amount? Somewhere between minus 20 to plus 20 milliseconds with respect to trial ID, right? Of course, it would be much smaller than this because you have trial IDs from 1 to 500. So the change is not going to be as large as 10 milliseconds, but you are allowing the possibility between minus 20 and plus 20, okay, which is fine. So this is your prior on parameter beta. So beta can take values anywhere between minus 20 and plus 20. And that's your prior assumption. Okay. So now your model is ready. This is an updated model, and this model encodes the assumption that average reaction time changes as trial ID changes. Okay. What you will do now? Well, now you fit this particular model to the data and estimate these three parameters. How do we do that? So one way is, of course, you can use any of the computational samplers that we talked about. If you want to do it in BRMS, then you will define the model like this. So model is like this, that in BRM, reaction time is given by 1 plus trial ID. So this is the format. You write a regression model in BRMS. 1 means the intercept, trial ID is the predictor, we call it the predictor. What is this? This is the outcome variable. This is the predictor variable. So the variable that we are using to predict the outcome, right? So this is the predictor variable. There are also other names. This is called IV, independent variable. This is dependent variable. Okay, or you can call it predictor variable, or this is the outcome variable. Okay, so this is how you write a regression model in BRMS. So RT predicted by 1 plus trial ID. Then you define the likelihood assumption, which is this is a normal distribution for RTs. And then for priors, you will have 3 priors, not 2, right? So there will be prior for alpha, beta, sigma, beta, alpha, right? So you will need to define 3 priors, right? So whatever prior to define, first will be for the class intercept, that is the prior for alpha. Second will be for class slope. So basically this is the slope parameter, right? So actually the class for these parameters is, I think, B. So you just need to write B, class equals to B. And the third one is sigma. So class equals to sigma. So this will be prior for this parameter. Okay. So this is how you define the priors. Okay. And now the model will give you estimates for alpha, beta, and sigma. Okay. So this is how a simple linear regression model works, right? In next class, we will practice regression model in R using BRMS package. But for now, I want to take another example. Okay. So this was the case of when you wanted to model judgment times. What if in the same task where you get the key, let's say the boys arrived, the task is to judge a sentence, okay, and the participants will make a response either yes or no, whether it is acceptable sentence or not, right? What if you are interested in modeling whether the judgment was correct or not? So you're interested in modeling the judgment itself, which can take value 0 or 1. 0 if the response was incorrect, 1 if the response was correct. So how do you model judgment itself, right, as 0 or 1, right? So simple model would look like this. The judgment in the ith trial comes from a Bernoulli distribution, right? You have done similar models before with underlying probability of success in ith trial being theta, right? And on theta you can have a prior, let's say beta 80-20 or something. This is typical model that we use. Okay, but what if someone makes the same kind of hypothesis that as trial ID increases, people get better and better because of practice effect. They get better and better at judging these sentences. So their judgment itself gets better and better. So that means their probability of judging a sentence is increasing. Okay. So as trial ID increases, judgment gets better. So how we encode this assumption in the model? Okay. So we'll try a similar thing as we did for the reaction times. So let us try to update the model. So judgment in the ith trial comes from Bernoulli theta I. Okay, fine. So why we are writing theta I? Because we cannot now assume that theta is constant across trials, because the probability of producing correct response is going to increase as trial ID increases. That's our hypothesis, right? Now theta I should be written as a function of trial ID. Okay. So can we write theta I in similar to reaction times, right? Can we write theta I equals to alpha plus beta into trial ID? Can I write this? Basically now this will become my new likelihood assumption, these two statements. So there is of course no problem in writing this. You can have a model like this, but there is a technical problem here, right? There is no problem in terms of, let's say, hypothesis or model, but there is a serious technical problem here. And what is that? Problem is this, that this parameter theta I can only take values between 0 and 1. So the parameter theta is constrained to take values between 0 and 1. And when we define a linear function like this, that theta equals to alpha plus beta into trial ID, it is very difficult to ensure that theta would have values between 0 and 1. Because what if beta has a large value, and let's say the alpha, initially alpha is let's say 0.3 and beta at some value let's say 0.05, okay, then easily this can go over 1 as trial ID increases. Similarly, if beta takes negative value, it can easily go below 0, 1, right, below 0 as well, right. So it's very difficult to control this the constrained space of parameter theta given this linear function. Okay, so what do we do in this situation? You need to apply some transformations such that theta never goes below 0 and above 1. And how do we apply the transformation? What you can do is this, that you define a logit, you transform theta onto a logit space. Okay, logit space is basically log of theta I divided by 1 minus theta I. Okay, now this transformation of theta is in an unconstrained space. Okay, so this function can take any value between minus infinity and plus infinity. I will show the properties of this function. And now we set up the regression like this. So log of theta I divided by 1 minus theta I equals to alpha plus beta into trial ID. Another way of writing the same thing is theta I equals to logit inverse logit of alpha plus beta into trial ID. Basically, I have written the same statement in a different form using inverse function. Okay, this is what we call sigmoid function. You might have seen this in logistic regression. Okay, so this is called a sigmoid function. Okay. So this is called a logistic regression, where you write the model like this. Ji comes from Bernoulli theta I, where logit of theta I equals to alpha plus beta into trial ID. Okay. So this is a logistic regression. There is a name for this regression. Right. Why this function helps? So actually what happens is that if let's say on x-axis you have theta, which has values between 0 and 1 here, okay, and on y-axis let's say you have logit theta. So the relationship is like this, that at theta equals to 0.5, value of logit theta is 0. You can check it. So at 0.5 divided by 0.5, it would be 1. Log of 1 will be 0. So at 0.5 it is 0, but as you increase it towards 1, the value increases slightly linearly up to this point, and then it sharply goes towards infinity. Okay, but it never reaches there, so it tends towards infinity sharply, right. In this direction it remains linear up to some up to a certain extent, and then it decreases sharply in this direction. So it goes from minus infinity to plus infinity, but within a reasonable range between let's say within minus 2 and plus 2, it remains linear. Okay, so that's how the function behaves, right. We'll see more about logistic regression later when we practice it, right. So this is a basic introduction to regression modeling in the Bayesian framework. In the next lecture, we will practice regression modeling using BRMS package. All right, so I'll stop here and see you in the next lecture.